In this video, we're going to look at the half reaction method for balancing redox reactions. And so here I have listed the steps that we need to take to use this method, and it may seem a little bit overwhelming at first, but I think once you've done a couple of examples, it's actually not quite so bad. And if you want another copy of this list, it's posted on the slides that are on D2L. So if we take a look at our first reaction, the first thing we want to do is assign oxidation states to each element in each compound in the chemical reaction so that we can determine what was oxidized and what was reduced. And so I'm going to do this pretty quickly. If you want a review of that, you can look at my video on assigning oxidation states. So the manganese is +4, oxygen will be -2, the aluminum is 0, this manganese is obviously +2, and the aluminum is +3. So we can see that the one that was reduced was the manganese because it went from +4 to +2. So my reduction half reaction will involve the MnO2 on the reactant side and the Mn2+ on the product side. So my reduction half reaction, unbalanced at least, is there. And then the oxidation half reaction, we can see that aluminum was oxidized. It went from 0 to +3. So my oxidation half reaction is going to be all right, and we'll treat these reactions in order. So first we'll balance the reduction half reaction. And so the first thing I want to do is balance the elements that aren't oxygen and hydrogen. And in that case, I've got one manganese and one manganese. So we're good. The next thing I want to do is I want to balance oxygens by adding water. And so I have 2 oxygens on the reactant side. I have no oxygens on the product side. So in order to get 2 more oxygens over here, I'm going to add 2 waters. All right, the next thing I want to do is balance hydrogens. I do that by adding H+. Since I have 4 hydrogens on the product side and no hydrogens on the reactant side, I'll need to add 4 H+ over here. All right, the last thing I need to do is balance the charges, and I do that by adding electrons. And so if I look on my reactant side, my total charge is 4 times +1, and then this one is neutral. So the total charge on the reactant side is going to be +4. The total charge on the reactant side is +2. And so when I add the electrons, they're going to make whatever side I add it to more negative. So I'm always going to add the electrons to the more positive side. So I have I have +4 and +2. So if I add 2 electrons to this side, then it will drop it down to +2, and it will be same as the charge on this side. So I'm going to want 2 electrons. All right, so at that point, the first half reaction is balanced. And now I'll follow those same steps to balance the oxidation half reaction. So in this case, the non-oxygen hydrogen elements are aluminum, and I have 1 and 1, so that's balanced. I have no oxygens and hydrogens to worry about, so all I need to do is get the charge balanced. And so my charge on the left-hand side is obviously 0. It's +3 on the product side, so I'll need to add 3 electrons to balance the charge. And if you notice, when I added the electrons, in the reduction half reaction, they're on the reactant side. In the oxidation half reaction, they're on the product side. That will always be the case. The electrons have to be on different sides of the 2 half reactions. Now to give myself a little bit more space, I'm going to go to a new slide. All right, so the 2 half reactions that we balanced on the previous slide are shown at the top. And so what I need to do now is I need to add my 2 half reactions back together to get the complete reaction. But in doing that, I need the electrons to cancel out, right? Or the electrons on the reactant side of the reduction half reaction have to be the same as the number of electrons on the product side in the oxidation half reaction. And so in order to do that, I'm going to have to multiply the whole half reactions by some constant so that the electrons are going to cancel out. And so I have 2 electrons and 3 electrons, so the lowest common product of 2 and 3 is 6. So in order to make 6 electrons here, I need to multiply the whole thing by 3. And then I need to multiply this whole half reaction by 2. And so now I'll add up, after I multiply by 3 and 2 respectively, all of the reactants in both half reactions will be the reactants in the overall reaction when I combine them. And then all the products multiplied by the respective constants will end up on the product side. And so what that's going to end up looking like is the following. Three times 4 is 12. And so I don't run out of room, I'll do the products down a little bit lower. All right. Now what I want to do is anything that is the same on both sides, I can cancel out. And so in this example, the only thing that appears on both sides of the reaction are the electrons. And the electrons have to cancel out. If the electrons don't cancel out, we've done something wrong. So 6 electrons cancels with 6 electrons. And so our final balanced redox reaction will be everything but those electrons. All right, and so our reaction should be balanced at this point, but it's always good to check. So you want to make sure that I have the same number of atoms on both the reactants and product side, and also that the total charge on both sides of the reaction is the same. And if that is the case, then I know that my reaction has been balanced. So I've got 12 hydrogens, 6 times 2, I've got 12 hydrogens. I've got 3 manganese, I've got 6 oxygens, 6 oxygens, 2 aluminums, and 2 aluminums. And the total charge on the reactant side, I have 12 H pluses, and the other 2 are neutral, so I've got plus 12. And here I've got 2 times 3 plus 3 times 2. That adds up to positive 12 as well. So this is my balanced redox reaction. If you want to see another example, I'll post a second video with an additional example.